Hello friends, welcome to the course Essentials of the Data Science with R Software 2, where we are trying to understand the topics of sampling theory and linear regression analysis. And in this module on the linear regression analysis, we are going to continue with our chapter Simple Linear Regression Analysis. So in this lecture, we are going to consider another method of estimation for the regression parameters as well as the variance. So you may recall that up to now we have considered the principle of least squares, and we have used the direct regression method estimation to obtain the value of the regression coefficients as well as the variance of the random error component. In statistics, there are different types of estimation methods which are based on different types of concepts, different types of philosophies, and among them, one very popular method is maximum likelihood estimation. So today we are going to discuss about the maximum likelihood estimation, and then we will talk about the test of hypothesis. So first, what is this maximum likelihood estimation? You see, likelihood means what? The literal meaning of likelihood is what? It is related to the probability, that what are the chances. So you are trying to say maximum likelihood means what are the maximum chances? Chances of what? So we are trying to draw a sample from some population. So now we need to assume a form of the population. So we will assume that suppose your sample is coming from a normal population with some finite mean and finite variance, and now we are assuming that this sample is truly representative of the population. So that means whatever you expect from the population, that should be present in the sample also. So that means now you are trying to observe the sample and you are trying to estimate the most probable value of the parameter that may happen, right. So in order to obtain the maximum likelihood estimation, what we try to do? We try to maximize the probability, and we try to obtain the values of the parameters which are most probable to occur. And this is the basic idea about the maximum likelihood estimation. So what we have to do? We simply have to write down the probability density function of all the observations, and then we have to maximize it, because the probability distribution functions are going to give us the probability of occurrence of certain events. So now we are going to maximize this probability, and we will try to find out the values of the parameter for which this probability will be maximum. So now if you try to see, once you talk about maximization, so in finite sample I can assume a nice probability distribution in which means we can do some algebra and we can find some exact expression of the maximum likelihood estimators. But in data sciences, what you can do, that you can use different types of algorithm also if you are dealing with some complicated distribution which is not necessarily normal. So you can consider those things, you can employ different types of optimization technique, and the basic objective is this: you simply have to maximize the likelihood or maximize the probability, right. So first we try to talk about the maximum likelihood estimation, and then I will give you the brief introduction to the test of hypothesis. Although I am assuming that you have a sufficient background in statistics, so all of you are familiar with the concepts of maximum likelihood estimation and test of hypothesis. So let us begin our lecture from this slide. Right. Okay. So now we are going to consider the maximum likelihood estimation of the parameters beta 0, beta 1 and sigma square. You can recall that we had taken a model y is equal to beta 0 plus beta 1 x plus epsilon, and epsilon had mean 0 and variance of epsilon was sigma square. So these are the three parameters in which we are interested. So, now we are making one assumption that we are trying to associate a probability density function with epsilons, because unless and until you associate a probability density function, you cannot write down the likelihood function. So, we assume that epsilon i's are identically and independently distributed following a normal distribution with mean 0 and constant variance sigma square. Right. So, first I try to give you the final outcome and then I will try to show you how to get them. So, when we try to find out the maximum likelihood estimators of beta 0, beta 1 and sigma square in the linear regression model, this I is equal to beta 0 plus beta 1 xi plus epsilon I goes from 1 to n. Then the maximum likelihood estimator of the beta 0 interceptum turns out to be y bar minus beta 1 tilde x bar. So, you can see here I am using here a symbol here b1 tilde. So, that is really going to indicate that this estimator is different from b1. So, we had earlier denoted b0 and b1 for ordinary least square estimator, and we will denote b0 tilde and b1 tilde for maximum likelihood estimator. So, the estimator of beta 1 slope parameter turns out to be summation I goes from 1 to n xi minus x bar yi minus y bar divided by summation I goes from 1 to n xi minus x bar whole square, which is the same as sxy upon sxx. So, you can recall that these two estimators of beta 0 and beta 1, which are the maximum likelihood estimators of beta 0 and beta 1, they are the same as ordinary least square estimator, right. Okay. Now, if you try to estimate the variance sigma square, then the maximum likelihood estimator of sigma square comes out to be summation yi minus b0 tilde minus b1 tilde xi whole square divided by n. And this we are denoting by here s square tilde. Now, you can see this is different from the ordinary least square estimator of sigma square. What is the difference? You can see here this numerator part is same as of OLSE, but if you come to denominator is different. What is the difference? In case of ordinary least square estimator, this denominator was n minus 2, but here it is n. So, the maximum likelihood estimators and ordinary least square estimator of beta 0 and beta 1 are the same, whereas the ordinary least square estimator of sigma square and the maximum likelihood estimator of sigma square, they are different. So, now we try to see how these estimators have been obtained. So, we try to have a sketch of the proof of maximum likelihood estimators. So, one thing you have to remember that when you are writing that epsilon I is following a normal distribution with mean 0 and variance sigma square, then the probability density function of epsilon I will be given by 1 over sigma square root of 2 pi exponential of minus 1 upon 2 epsilon I minus mean 0 divided by sigma whole square, right, where your epsilon lies between minus infinity and plus infinity. So, this is actually the probability density function of normal 0 sigma square. Now, you are assuming that epsilon i's are independent. So, when they are independent, then the joint density function of epsilon 1, epsilon 2, epsilon n, this can be written as the product of the individual probabilities, probability density function I goes from 1 to n. And once you are assuming that epsilon i's are, they are identically distributed identically means all epsilon 1, epsilon 2, epsilon they have got the same distribution with mean 0 and variance sigma square, right. So, this can be written here as a f of epsilon I raised to the power of here n, right. So, this is the basic concept which I am going to use here, right. And you can see here that this epsilon I is your y I minus beta 0 minus beta 1 x I. So, that is what I have written here. I have written the joint density function of epsilon 1, epsilon 2, epsilon n in terms of x I, y I, beta 0, beta 1 and sigma square. So, you can see here this is the same thing, this is the square root of 1 over 2 pi sigma square and exponential of minus 1 upon 2 sigma square. This is your here epsilon I minus 0 and divided by 2 sigma square, right. So, what we try to do here that we have to now maximize this likelihood function and we have to obtain the values of beta 0, beta 1 and sigma square. So, we know that this likelihood and the log of likelihood both are monotonic functions. So, instead of maximizing the likelihood function, I can maximize the log likelihood also. So, that is going to give us the same outcome. So, now I consider here the log of this likelihood and I try to write down here this quantity will become minus n by 2 log of 2 pi, that is I am taking here natural log is denoted by ln, okay. And this quantity here becomes here say here minus n by 2 log of sigma square and 1 upon 2 sigma square is minus 1 upon 2 sigma square and then this quantity from here, okay. So, now this is the log likelihood which I have to maximize. So, I try to use here the principle of maxima and minima and I try to partially differentiate this log likelihood with respect to beta 0, beta 1 and sigma square. And once I try to differentiate the log likelihood with respect to beta 0, I obtain this result that you can verify, that is very straightforward. And similarly, when I try to partially differentiate log of likelihood with respect to beta 1, then I get this value. And similarly, when I try to differentiate the log likelihood or partially differentiate the log likelihood with respect to sigma square, then I get here this value. Now, I try to equate them equal to 0. So, that is what I am doing here, all the 3 equations have been equated to 0 and these 3 equations are called as normal equations. Remember one thing, do not get confused that this word normal is coming from normal distribution. The normal in normal distribution and the normal in normal equation, they are different thing, right. Even if you try to take here any other distribution say binomial or Poisson also, even then you will have normal equations. These are the 3 normal equations that we have obtained, and if you try to see what is this thing, this can be written as I goes from 1 to n summation y I minus beta 0 minus beta 1 x I equal to 0, and this equation can be written as I goes from 1 to n y I minus beta 0 minus beta 1 x I times x I equal to 0. And now, can you really recall, have you ever solved these equations earlier? They are the same equations as in the case of least square estimation. When you obtain the ordinary least square estimate, you solve the same equation. So, now I do not need to solve it again, right. So, if you try to solve them, they will give you here beta 1 tilde to be Sxy upon Sxx, and which I have denoted by see here B1 tilde, which is the maximum likelihood estimator of beta 1, and the maximum likelihood estimator of beta 0. This is beta 0 tilde, this is y bar minus B1 tilde x bar. Now, if you try to solve this equation and try to substitute beta 0 equal to b 0 tilde and beta 1 equal to b 1 tilde in this equation and try to solve here. You will get here the value of sigma square, that will be your estimate, which is denoted as s squared tilde, that will be your here 1 upon n summation I goes from 1 to n y I minus the value of beta 0, which is b 0 tilde, minus the value of beta 1, which you have obtained as b 1 tilde x I whole square. So, you can obtain these things, and yeah. So, these are the final expression that you will get. So, these are the values which are expected to maximize the likelihood function, but how to cross check it? So, for that I will not do it here, but I will try to do it in more detail when we will try to consider the multiple linear regression model. But here you can find out the second order partial derivatives of the log likelihood, something like you have find out the log of L, try to find out the second order derivative with respect to beta 0, beta 1, sigma square from where? From here, right. From these three equations you try to differentiate them once again, you will get the second order partial derivatives, and then try to create the border Hessian matrix, and then you can show that these three values of beta 0, beta 1 and sigma square that you have obtained, they are maximizing the likelihood function. Hence, these three values can be called as the maximum likelihood estimators of beta 0, beta 1 as well as sigma square, right. Okay, so, this was all about the maximum likelihood estimation. Now, I try to come on different aspect, which is test of hypothesis, right. So, before I do, let me try to give you some idea. So, the first question is, why do we conduct the test of hypothesis? And sometimes people get confused between the estimation and test of hypothesis. Now, you see, you have employed two different estimation methods to estimate the same parameter beta 0, beta 1 and sigma square. Fortunately, and just by chance, the estimators for beta 0 and beta 1, they come out to be the same. The OLSE as well as MLE, they are the same for beta 0 and beta 1, but that is only by chance, means it is not a rule that these estimators are going to be the same. But you have seen that the variance estimator for OLSE and MLE, they are different. So, now whatever estimation technique you use, they are based on the random sample. You are simply trying to find out some mean, some sum of squares, and then you are trying to compute the value of parameter. Now, suppose the sample changes. You have seen through the theory of sampling theory that as soon as you draw a different sample, you will get different values of the statistic. So, now the question is, different samples will generate different types of values of these parameters. So, the question is, which one is right, which one is wrong, and various types of questions crops up. So, we assume that as long as we are getting the random samples and the difference in the values of these parameters that we are obtaining, that is just due to random variation, we can accept it, because we have no other option. The random variation is beyond our control. But if there is some assignable cause, that should be taken care, right. So, what we try to do here, that we try to find out the values from the sample, and then we try to compare them with some given values. And based on that, we try to make a comment whether the estimated value can be considered to be the same as the value which we have assumed, or it is known to us. That is the main objective of test of hypothesis, and what I am doing is this a very layman language. right. I am not explaining you here the basic concepts of test of hypothesis, right, that I assume that you know it. So, one thing which I would like to clear, that many times people get confused that the test of hypothesis can also give us the values of the parameter. The answer is no. The values of the parameter can be obtained only through the estimation methods. The test of hypothesis can only check whether the estimated values are equal to or less than or greater than the given values. So, the test of hypothesis is conducted against some known values, but if the hypothesis is not accepted, then the methodology of test of hypothesis will not help us in identifying or knowing that, well, what is the correct value. The question goes, suppose you estimate something and I say, okay, suppose you estimate the sample mean to be 20 and I assume that the population mean is suppose 30. Well, and if the difference is due to the random causes, and suppose the hypothesis is not accepted. So, that means I will be concluding that the sample mean and the population mean are different. Now, you can ask me next question, okay, you are saying that, okay, these two values are different, that I am accepting, but please tell me what is the correct value then. Then I will say sorry. The test of hypothesis cannot answer this question. That you have to look into your estimation method, the properties of estimation techniques, and then you have to decide that what can be a better value which will be close to the true value. Okay, so, that is the basic idea. Now, we are estimating here three quantities, beta 0, beta 1 and sigma square. So, we would like to conduct the test of hypothesis for all these three parameters. In this chapter, I am trying to show you that how you can conduct the test of hypothesis for this single parameters, and in the case of multiple linear regression model, I will try to extend this concept of test of hypothesis in testing the equality or something like this for more than one parameters also. Right. And after this, I will try to consider the confidence interval. What is confidence interval? For example, you have utilized the principle of least square and method of maximum likelihood to estimate the values of beta 0, beta 1 and sigma square. Well, these estimation techniques are giving you one particular value, the value of these parameters at a point. So, these are actually point estimate. Point estimate means you are trying to say that okay, the value of this parameter is this, but now the other alternative is this. I can find a probable interval in which the population parameter value will lie. Right. The most simple example goes like this. For example, if there is a medicine and we conduct an experiment to know that what is the approximate number of hours by which the medicine can control the fever. You take a sample and suppose you find out the sample mean and then try to compute the statistics, and suppose you come to know that the value of the parameter is suppose 6 hours. So, that means that medicine is expected to control the fever for 6 hours. But do you think that this 6 hours is going to be the same for all the persons? In some persons the medicine may be effective for say 5 hours 30 minutes, in some persons the medicine may be effective for 6 hours 30 minutes, in some persons the time may be smaller than 6 or more than 6 also. Right. So, for that if I say okay, this medicine can control the body temperature or fever say from 5 to 7 hours. This also makes sense. What is this? This is confidence interval estimates. That means, we are trying to find out the value of the same parameter not at a point, but in the form of an interval. So, for the interval there will be a lower limit, there will be an upper limit. So, our objective here is this. We already have now learnt that how to estimate the parameters at a point. Now, we will consider how to estimate them in an interval. Right. So, first we try to consider the test of hypothesis, and then we come to the confidence interval estimation, and you will see at a later stage that confidence interval estimation and test of hypothesis both are actually interrelated through something. So, let us now come back to our slides. Okay. Now, we try to assume that we will be working under the normal population. This normal population will have some mean and will have some variance sigma square. So, we have here two possibilities, that this sigma square is known or sigma square is unknown. So, we will consider here two possible cases, and we will try to construct the test of hypothesis and confidence interval estimation under two possible cases, when sigma square is known and when sigma square is unknown. So, our model is going to be the same, y I is equal to beta 0 plus beta 1 x I plus epsilon I, and we have got a number of pairs of observation, and we assume that these epsilon i's are independent and identically distributed, which are following a normal distribution with mean 0 and variance sigma square. Okay, so, now let me first consider the construction of test of hypothesis for the slope parameter beta 1, and the first case I try to take when sigma square is known, and our H naught, which is null hypothesis, is beta 1 is equal to beta 1 naught. So, beta 1 naught is some known value. Right, I can write down here, say H naught beta 1 is equal to 2, or H naught beta 1 is equal to 100, whatever you want. So, you want to test that the values which you have obtained from the sample for this parameter beta 1, are they equal to the value beta 1 naught in the population or not. Right. So, this is our now setup, that beta 1 0 is some given constant. Now, if you remember, in the case of ordinary least square estimation, we had already proved that the estimators B 1, that is the least square estimator for the parameter beta 1, is an unbiased estimator, and its variance was obtained like this. Right. And we also had shown that B 1 was a linear combination of y i's, and now we are, since we are assuming here that epsilon i's are following normal 0 sigma square. So, will be y I will be also be a normally distributed random variable. Why? Because the linear combination of normally distributed random variable under certain condition is also normal, and what will be the mean of y I? Mean of y I will be beta 0 plus beta 1 x I, because you are assuming x I to be fixed and epsilon I has mean 0. So, this will be here the mean beta 0 plus beta 1 x I, and what will be the variance of y I? That will be variance of beta 0, which is constant. So, 0, variance of beta 1 x I, which is constant. So, 0. So, that will be same as the variance of epsilon I, which is sigma square. So, I can write down here that y I follows a normal distribution with mean beta 0 plus beta 1 x I and variance sigma square. And if you can recall that we had expressed B 1 as summation k I y I, right. I am not going into the details once again. So, based on that, I can write down from here that B 1 has got a normal distribution whose mean is beta 1 and variance is sigma square upon S x x. Well, before I go further, let me clarify that I just finished the topic of maximum likelihood estimation, and then I started the test of hypothesis. So, please do not get confused that the test of hypothesis is based only for the maximum likelihood estimator, right. Means that can be done for the ordinary least square estimation also, and you have seen that at this moment we are trying to construct the test of hypothesis and confidence interval for beta 1 and beta 0, which have got the same estimate in under the setup of least square estimation as well as maximum likelihood estimation. Now, using this result, we can construct the statistics that B 1 minus beta 1 naught divided by the standard error or standard deviation of B 1. So, which is here like this square root of sigma square upon SXX, and this will follow a normal distribution with mean 0 and variance 1 when H naught is true. Right, there is a strong theory, all those derivations we have in statistical inference, but we are not going to discuss those things here. You can just believe on me that this statistics will follow a normal 0 1 distribution under H naught. As soon as I say under H naught, that means when H naught is true. So, this sentence and when H naught is true, sometime you will see that it is written in the book, or sometime even I may use as under H naught. So, that is the same thing, right. So, now the decision rule to accept or reject H naught will be that reject H naught, the H naught here is beta 1 is equal to beta 1 0 against H 1, beta 1 is not equal to beta 1 naught at alpha level of significance if p value is less than alpha. Okay. Means I can just give you one thing, that when you try to conduct the test of hypothesis, then you have the sampling distribution of this statistics Z1, which is say here normal 0 1. So, we try to fix here alpha. So, it is a two sided test of hypothesis, because we are trying to take here not equal to. So, this region in the mid, which is here the dotted region, this is the acceptance region, and the shaded region here, this is the region of rejection. So, what we try to do? We try to find out the critical value from the table of normal 0 1, which is here, this is the critical value, and this is here the critical value, and we try to see whether the calculated value of Z 1, which is here, whether this lies in the region of acceptance or region of rejection, and based on that we try to take a call whether H naught is going to be accepted or not. So, this is the basic fundamental, that is the theory, but since we are going to work in the software, so the softwares usually give the outcome in terms of p value, and then in that case the rule is that reject H naught when p value is smaller than alpha. So, since we are going to do all the things on the R software, so I will not be considering the classical approach of test of hypothesis, which is based on the tabulated values of either normal, t, chi square, f, etc., but I will be depending more on the p value. So, all the results whatever I am going to do here, they will be the based on p value. What is the p value? The p value is the smallest level of significance at which H naught would be rejected. And when I say that H naught is accepted, then accepting H naught means that the difference between the sample value and the hypothetical population value is not significant, right. Okay. Now, I try to come to the construction of confidence interval under the same setup when sigma square is known. So, we know in the case of confidence interval what we try to do, we try to obtain here the lower limit and we try to obtain here the upper limit, and suppose my confidence coefficient is 1 minus alpha. So, usually when we are trying to consider a symmetric distribution like as normal 0 1, then on the both side this shaded region will be alpha by 2 and this dotted region in the mid will be 1 minus alpha, right. So, these two values lower and upper limit, they are going to give us the values of the confidence interval. So, they are the lower and upper limits of the confidence interval. So, our objective is this, we want to find out these values based on the statistics. So, what we try to do here, that we
are assuming that my confidence coefficient is 1 minus alpha. So, 1 minus alpha % confidence interval for beta 1 can be obtained in this case using the Z1 statistics, right. So, Z1 is your nothing but B1 minus beta 1 divided by standard deviation of B1. So, what we assume that this capital Z1 will be lying between minus z alpha by 2 and plus z alpha by 2. What are this minus z alpha by 2 and plus z alpha by 2? They are the say 100 alpha by 2% points on the distribution of normal 0 1, right. So, what we try to do, we simply write to this statement that the probability that the capital Z1 will be lying between the critical values minus z alpha by 2 and plus z alpha by 2, and the probability of this event is 1 minus alpha. So, now I can rewrite here it like this. Now, you can see here I simply have to simplify it. You can write down this thing here B1 minus beta 1 upon square root of sigma square upon SXX, which is lying between minus z alpha by 2 and z alpha by 2, and this can be written here as say B1 minus beta 1 lying between say minus z alpha by 2 and square root of sigma square upon SXX, and here z alpha by 2 and square root of sigma squared upon SXX. Now, if you try to solve it here, now this beta 1 will be lying between these two limits which we have obtained here. So, that is the usual approach to obtain the confidence intervals. So, you can see here now I have obtained the probability that beta 1 will be lying between these two limits, and this probability is 1 minus alpha. So, this value here, this is the lower confidence limit, and this value here, this is the upper confidence limit. So, lower confidence limit, and the second one is upper confidence limit of the confidence interval, right. So, I can write down finally that the 101 minus alpha % confidence interval for beta 1 is given by these two limits, where z alpha by 2 is the 100 alpha by 2% points on the normal 0 1 distribution. So, you can now see this you have computed, you can obtain it from the software. This is known to us. This you can compute on the basis of given sample of data. This you can obtain from the table. So, you can compute this entire limit. Similarly, you can compute the upper limit also, and thus you can compute the entire confidence interval. So, you can see here it is not difficult even if you want to compute it manually, but definitely we are going to use it on the software. And now I come to the second case where we assume that sigma square is unknown, and we try to construct the hypothesis for the same parameter beta 1, right. So, my hypothesis remain the same, H naught beta 1 is equal to beta 1 naught, where beta 1 naught is some given value or given constant. So, since we are assuming that sigma square is unknown, so we have a result from statistical inference that SS res upon sigma square follows a chi-square distribution with n minus 2 degrees of freedom. And if you remember, we had already used it in the earlier lecture when we were trying to estimate the value of sigma square based on the least square estimation, and we had obtained there that expected value of SS res divided by n minus 2 is sigma square, right. So, now actually I can also prove that if you try to see here that this is your here SS res and V1 was your SXY upon SXX. These two quantities are independently distributed, although I am not proving it here, but that is pretty simple and right. So, and if you can show that these two are independently distributed, which are actually independently distributed, you can try, then B1 minus beta 1 0 divided by standard error of B1, which is here square root of sigma square hat SXX. Sigma square hat is what? This is from here you can write down sigma square hat is SS res divided by n minus 2, and if you try to write down this statistic, this will follow a t distribution with n minus 2 degrees of freedom when H naught is true. Right. So, this simply follows t with n minus 2 under H naught, that is when H naught is true. So, now I can frame the decision rule, which is pretty simple, that reject H naught beta 1 equal to beta 1 naught against H 1 beta 1 is not equal to beta 1 naught at alpha level of significance if p value is less than alpha. Okay, before I go further, let me try to clarify one point. In this test of hypothesis, in this chapter, we are mostly interested in testing the alternative hypothesis, which is of the form of not equal to, that is two-sided alternative hypothesis. Actually, this test of hypothesis is going to play a very important role when in the variables collection and in knowing whether a variable is important or good or bad. Right. So, that is why we are considering here only the two-sided test of hypothesis. Otherwise, the left tail test or right tail test, something like beta 1 is greater than beta 1 naught or beta 1 is less than beta 1 naught, these type of hypothesis can easily be done exactly on the same line using the same statistics. So, do not get confused that why I am not considering here other type of test of hypothesis, they can be done exactly on the same way. And similarly, if you want to construct the confidence interval, exactly you have to follow the same thing. Now, I will assume the 101 minus alpha % confidence interval for beta 1 can be obtained using the T0 statistics, and we assume that this T0 lies between minus T alpha by 2 and plus T alpha by 2, where these two values are the critical values which are obtained from the T tables, that is the tables for the T probabilities, and the probability of such an event is 1 minus alpha. So, you simply try to substitute here the value of T naught and just try to simplify it exactly in the same way as we have done here. Right, exactly in the same way as we have done here, try to simplify it, very simple, and then you will obtain here this inequality and the probability that beta 1 is lying between these two limits is equal to 1 minus alpha, and hence I can obtain the 101 minus alpha % confidence interval for beta 1 when sigma square is unknown as here like this. So, you can see here all these things can be obtained from the data, right, and about this here t value that can be obtained from the table, but anyway I am not going to show it here manually because we are going to use the software. So, here what is this thing? This T alpha by 2 is the 100 alpha by 2% points on the T distribution with n minus 2 degrees of freedom. Okay, now, I come to the test of hypothesis for the beta naught. Now, the test of hypothesis and confidence interval for beta naught under the case of sigma square and sigma square when sigma square is known and when sigma square is unknown can be constructed and developed exactly on the same line as I have done for beta 1. The only thing is this, the variance of beta 0 and the estimate of variance of beta 0 hat, which is the variance of b 0 and variance of b 0 hat, they will be only changed, right. So, under this case you can see here we already have proved that expected value of b 0, which is the ordinary least square estimator of beta naught, this is an unbiased estimator of beta naught, and the variance of b naught can be obtained by this expression, right, that we already have obtained in the earlier lecture. So, now I can use the Z statistics and I can construct my statistics by b 0 minus beta 0 0, which is a known quantity here, which is a given quantity here, because my hypothesis is here H naught beta 0 is equal to beta 0 0 or beta naught naught or beta double naught you can say. So, this will also have a normal 0 1 distribution when H naught is true. So, you can write your here decision rule exactly on the same line that you reject this H naught against H 1, beta 0 is not equal to beta double naught at alpha level of significance if p value is smaller than alpha. And if you want to construct the confidence interval, you have to use the same technique, that Z0 which is given here like this is lying between minus z alpha by 2 and plus z alpha by 2, and the probability of such an event is 1 minus alpha. Right. So, you can simply solve this equation as we have done earlier and 2 times. So, and you will obtain the lower limit here by this expression and upper limit by this expression, and so I can say that the 101 minus alpha % confidence interval for this beta naught is given by these 2 limits. This is the lower confidence limit and this is the upper confidence limit. Right, and as usual this cut alpha by 2 is the 100 alpha by 2% points on the normal 0 1 distribution. And similarly, when sigma square is unknown, you know now. In this case, we will have a t statistics, and this statistic is given by b 0 minus beta double naught divided by the standard error of, this is the standard error of b 0, and if you try to find out using the rules of probability theory and probability distribution, this statistics will have a t distribution with n minus 2 degrees of freedom under H naught, or when H naught is true. So, now I can construct the decision rule that reject H naught against this two-sided H1 at alpha level of significance if p value is smaller than alpha. So, now you can see that now means everything is very similar. Once you have done the first case, doing all other cases have the same story, means everything is on the similar lines. And similarly, you can also construct the confidence interval. So, in this case, the T0, which is here this statistic, will lie between minus T alpha by 2 and plus T alpha by 2 at n minus 2 degrees of freedom, and the probability of such an event is 1 minus alpha. So, if you simply try to solve this inequality, you will get here this as your lower confidence limit and this quantity here as a upper confidence limit, and the probability of such an event will be 1 minus alpha. So, the confidence coefficient is 1 minus alpha. Hence, the 101 minus alpha % confidence interval for beta 0 can be obtained here like this. Right. So, now we have obtained the confidence interval and test of hypothesis for beta 0 and beta 1 under 2 cases when sigma square is known and sigma square is unknown. So, this is your here lower confidence limit and this is your here upper confidence limit. So, after this we consider the test of hypothesis and confidence interval for sigma square. So, the test statistics for sigma square is found using the result that sum of square due to residual divided by sigma square follows a chi-square distribution with n minus 2 degrees of freedom. So, based on this, the test statistics for the hypothesis H naught sigma square equal to sigma naught square, where sigma naught square is some known value, given value, constant, can be constructed, and the final statistics comes out to be like this: chi square c, I am using here c means calculated, which is summation I goes from 1 to n yi minus y bar whole square divided by sigma naught square. So, this value can be obtained from the sample and this value is known. So, whole this chi square c statistics can be found manually also, and this statistics will follow a chi-square distribution with n minus 2 degrees of freedom under H naught, that is when H naught is true. Okay, so, based on this, the decision rule can be made as reject H naught against H1, two-sided hypothesis at alpha level of significance if p value is smaller than alpha. Same thing what we have done earlier, and you can also construct the confidence interval using the same result, but now here you have to be careful. Normal and t distribution, they are symmetric like this one, symmetric around their mean value, right. But for chi-square is not a symmetric distribution and it has different shapes depending on the degrees of freedom like this, right. When even the degrees of freedom is less 1, 2, 3, 4, then even the curve is like this. So, in this case you cannot have a structure like that alpha by 2 on the same end side will have the same value on the x axis like we have done earlier, that minus z alpha by 2, then this is going to be plus z alpha by 2. This will not hold, but in this case what we are going to do, suppose this is here, see here alpha by 2, then this is here 1 minus alpha by 2. So, you have to actually look into the book that how they are trying to consider. Sometimes they take this area on the left hand side to be 1 minus alpha by 2 and right hand side area to be alpha by 2. So, you have to just check before you read a book. So, in this case we are simply trying to say here, suppose this is my here chi square value with alpha by 2 and this is here the value which is chi square 1 minus alpha by 2. So, now I can say here that this statistics SS res upon sigma square will lie between these two limits on the chi square distribution, and the probability of such an event will be 1 minus alpha. And if you simply try to simplify this inequality, you get here these two limits. So, this is going to be the lower confidence limit and this is going to be the upper confidence limit, and this will come out to be SS res divided by the corresponding value of chi square at 1 minus alpha by 2 level, significance level, and SS res divided by chi square value at alpha by 2 significance level, and based on that the 101 minus alpha % confidence interval will come out to be like this. So, you can see here that this is a function of SS res, that is sum of square due to residuals, and here you have to be careful that, and always remember that chi square is not a symmetric distribution. So, now we come to an end of this lecture, although pretty long lecture, but my objective was to finish in a single shot, so that your time is saved and I do not have to repeat the things between two lectures. I hope you do not mind it. Well, you can means listen to it in two parts. Well, so my objective was here that I have given you the main idea about the test of hypothesis. Your question will be where it is going to be used. But believe me, for some time this is one of the very important tool in statistical modeling, particularly under the linear regression analysis, and I will show you later on that without this you just cannot work in linear regression analysis. Yes, sometimes students get confused that why I am trying to do all this theory, but when you come to multiple linear regression model, I am promising you each and everything whatever you have done, that will play a very important role, and without understanding these things you cannot do it. And my problem is this, here I can show you all the things, I can create a confidence interval, I can give you all the values individually, but in case of multiple linear regression model I will not be able to show you things more clearly, but you will have to assume, you will have to think in your mind that this is how the things will look like. That is the idea, right? So, have patience, have confidence on me, have faith on me, and try to revise it, try to see it, try to settle down this concept in your mind, and I will see you in the next lecture. Till then, goodbye.